So we're in your chemistry in chapter 17, section 2. And we're going to be talking about nuclear stability in this part of the chapter. It starts out talking about how there's unstable nuclides. And these nuclides basically have been synthesized in the laboratory, a lot of them. So out of the 264 of the 3,000 nuclides that have been synthesized, only 264 have been considered stable. So most of them are unstable. So the stability of an atom is determined by the number of arrangements of the protons and neutrons in its nucleus. So when we're talking about those that occur naturally in nature, most of the ones that occur naturally in nature are stable. But we've gone into the chemistry now of creating, synthesizing different types of molecules and nuclides at this point. So, and most of those are unstable. So this is really amazing to me about this part of this chapter. And I'll tell you why, because it has to do with a nuclear force that we don't know where it comes from, actually. So how did this nuclear force or these laws come into being? And what really holds together a nucleus? You know, because in a nucleus you have protons, and the protons, they are positive, and then you have the protons together with neutrons, which are neutral. But the protons, like charges, they're both positive. They'd be forcing each other apart. But there has to be a force that holds together the nucleus. And of course, this has to do with God, because, what kind of force is this? Well, it's a natural force. Is it a natural force or a supernatural force? But we don't know, but we call it a nuclear force in science. And this is what holds the nucleus together. And also, we call it a binding, binds the nucleus together. And when the binding power is overcome, and this nuclear force is overcome, it lets off energy, right? So let's talk about this a little more. So it says the 99.97% of the mass of the atom is in the nucleus. And so this means if you would lift a 50-pound weight, you are going to be lifting 49.99 pounds of atomic nuclei, with only 1/4 ounce of electrons. So basically saying, my goodness, if you have 50-pound weight, only 1/4 ounce is going to be electrons. Electrons are extremely light. However, the nucleus is really tiny, minuscule compared to the whole atom. So if a nucleus were the size of a marble, the atom would be the size of a large sports stadium. Can you believe that? A marble in the middle of a sports stadium, that would be the nucleus. And so it is estimated that the total volume of the atom is at least a trillion times greater than the volume of its nucleus. So the volume of this nucleus is so small. I mean, this nucleus is going to be so dense in comparison. So if 99.97% of the, or 99.97% of the atom's mass is contained within a trillion of its volume, this means you can imagine how dense. So the calculations revealed the density of the atom is about 2.8 times 10 to the 4th grams per centimeter per centimeter square. This is 25 trillion times denser than lead. Or if you took a soda pop can, and you had that solid nuclear matter in the soda pop can, it would weigh over 100 billion tons in a soda pop can that would contain the same amount of matter as a solid lead block, 1.3 miles on the side. Can you imagine how dense that is? So we're talking about extreme density in the nucleus compared to the rest of the atom. So here's a picture, the density of matter in the nucleus. If you compare, so you see how dense it would be. It'd be denser than all of the city of what city that is. It looked like it could be a big city. So that's how dense. saying over 100 billion tons. You know, if it was just, if you took the density of the atom and put it in a soda can of that size, it would weigh 100 billion tons. Oh my goodness. So the forces in the nucleus. So like charges, we know like charges repel each other with force. You know, basically we know that. If you take a magnet, like charges are going to repel. Unlike charges, opposite charges do attract. So we can see how the electrons, you know, going around would be attracted to the positive center. You know, we understand that. But what holds that positive center together? So as we think, there's the two protons here. It says basically the two protons in repelling. The repelling is unbelievable strong. In fact, it is like the repelling nature of these is like two protons here are 10 to the negative 15 centimeters apart, repel each other with electrostatic force of roughly 2.5 million newtons, or 560,000 pounds. This repulsion is 10 to the 36th times stronger than the gravitational attraction between the protons. So you're talking about, oh my goodness, you know, this is a surprising strength repulsion between protons leads to an important question. And that's the question we all have, don't we? What holds the nucleus together, for goodness sakes? And the answer is there's another force at work. And they call this force, now they label it as the strong nuclear force. You know, I just believe it's God that holds all of our atoms together, because the Bible says that. So that basically this acts on the protons and neutrons holding together. This force has exceeding short range, only 1/100,000th of a meter, but within the distance of it is 100 times stronger than the electromagnetic force by which protons repel. So protons want to repel, but the force, the strong nuclear force that holds them together is 100 times stronger to hold those atoms together. What if the atoms wouldn't be able to be held together? We would not even be here. We wouldn't even have matter if we didn't have atoms, right? So how important is this strong nuclear force? It is so important, but it's in like, where does this come from? Because of its strength, the strong nuclear force is able to overcome the natural repulsion between the protons, and that's what binds them together in the stable unit, this force. And despite all this, still not all arrangements of neutrons and protons are stable. Some are unstable. Unstable nuclides tend to undergo nuclear reactions that convert them into other nuclides. And basically that's man in chemistry making these this happen, you know, in the midst of this. This is the conversion of one nuclide into another in a spontaneous nuclear reaction. And this spontaneous nuclear reaction, this is a definition. This is called radioactive decay. So radioactive decay is the spontaneous nuclear reaction of that particle decaying. Kind of happened. Where did decay start? Probably in the Garden of Eden, right? So this conversion of one nucleotide to another takes time, and you'll find that, but it's called radioactive decay. And that's what we basically are doing in chemistry when we're trying to produce new nuclides and new elemental, you know, in the midst of a laboratory. So radioactive decay is almost always accompanied by emission of nuclear radiation. So whenever you have decay, you have nuclear radiation, which is energy, right? From that force, from that strong nuclear force given out in nuclear decay. It sounds familiar, just what the Bible is talking about to me. So radioactive decay is basically as the elements start decaying to the point where they'll decay enough to turn into another element, you know, in that point, that decaying process gives off radioactive energy, nuclear radiation. So I like what it says here. It says, the strong nuclear force, along with other forces of nature, is an important part of God's design for the universe. The Bible tells us that Jesus Christ, the Creator, is upholding all things by the word of his power. That's Hebrews 1:3. And that by him all things consist and hold together. Colossians 1:17. Although science can tell us some things about the forces and God's laws and established to govern the universe, we know from scriptures that it is ultimately God's power that sustains his creation. God's power holding us together, holding the world together. So this section talks about nuclear mass defect. And that's where we found out, if we get into science, we find out about Einstein and his theory of relativity, and everything goes in this nuclear mass defect. They couldn't figure this out either. So the nuclear mass defect, masses of subatomic particles are very accurate. We found that we can find out the masses so accurate. Here, if we have masses and we add protons, 8 protons, 8 neutrons, 8 electrons, we'll find that each one of these will add up to a total mass of 16.131921 units. However, if these same 24 particles are assembled into the into the nucleus, and they form oxygen, all these together will form oxygen 16, it has a mass of only 16.994915 units. It's missing a mass defect, because if you add, if you're saying, 8 plus 8, or say you're saying, 1 plus 1 equals 2, but 1 plus 1 equals 1 point, da, da, da. Anyway, so we're missing something here, and that's the defect. Like, how come if you take each one of these protons and each one of these nucleons and add them up to this, why doesn't the nucleus weigh at least this? But instead, it has this mass, and somehow 0.137066 units of mass disappears when the particles are assembled together into an oxygen atom. So when they're assembled together, you have an oxygen atom, and you take the protons, you take the neutrons, assembling, you're getting this, but this doesn't equal this. So this is where this mass defect is. And this is not just confined to oxygen. Other atoms do the same thing, exactly. And so scientists now call this phenomenon the nuclear mass defect, or the nuclear mass does not add up, right? So where does this missing mass go, since all these particles are present? Well, we didn't really understand this until the brilliant Jewish physicist Albert Einstein himself put together the theory of relativity, which we all know. What is that? E equals mc squared. And it can also be written as energy equals mass times the speed of light squared. So figuring that out. And one consequence of this relation says that we can now regard energy as having mass. So we know energy has mass. So when we're talking about energy, we can say the missing energy is actually what's causing the missing mass, this mass defect. So any quantity of energy has to be associated with mass. Here we have this with the speed of light here too. So according to interpretation of this, the object, interpreting would be the object gains energy, it gains mass, and when the object loses energy, it loses mass. We know that. So the equivalent mass of 1 joule of energy is approximately 1.1 times 10 to the negative 17th power kilograms, or 6.7 times 10 to the 9 units. So we have, okay, now we know this has something to do with the theory of relativity that they didn't understand back with that mass defect. So the mass of energy, so we have those, 8 protons, neutrons, and electrons, and they're assembled into oxygen. And we know that's 2 times 10 to the negative 11th of joule energy is released as heat and electromagnetic waves. And this mass of this energy being 0.13706 units, is equal to the missing mass. So if you take this energy into account, then mass is completely conserved, and there's we found it. So here we have, when we take all of this together, and we have 16.3192, and then the energy to put it together, we put in this energy in, as we're putting the mass of this energy in, it will add up that exactly to be. So this measurable mass defect also occurs in all of nuclear reactions. So for example, say you have the decay of an atom of uranium into thorium onto, and then that in helium, and releases that. You have this energy that's equivalent to the mass of 0.005 units. So comparing these mass, we find that the decay products are indeed 0.005 units lighter than the original atom, corresponding to the amount of energy released. So this whole thing with mass and energy is so amazing, and this is how Einstein could calculate this mass defect now that had to do with energy and mass. And so here you have, the equation here. So basically looking at this, you have 92 protons, uranium here, 92. You have 146 neutrons, 146 neutrons in that point, 92 electrons and 92 electrons. We're talking about what's going on here. So this takes 7.5 times 10 to the negative 13 joules. And so if you add these up, you get 238.051 units. And then this on this side, as the breakdown, you're going to get 238.046 units. But you're going to have to add that energy. And if you add the energy is going to add up to this number. So it's just basically to know that you're adding the energy, what we now are going to call the nuclear binding energy in, and that energy that's holding it together is so important, right? So going on here, it says, here's Einstein's mass energy equation here. E = mc squared in the midst of holding the ship together, right? So since matter can be converted to energy and energy into matter, the law of conservation of energy is also stated as the law of conservation of matter and energy. So we have conserving energy, but now it's also conserving matter and energy. What a deal. That matter is conserved too in the same way. Matter and energy cannot be created, nor cannot be destroyed, only changed from one form to another form. So in a nuclear reaction, energy does not appear out of nowhere. Instead, matter is converted into energy. And this is the law of the conservation of matter and energy. And this is obeyed. So now we know it works out. That strong nuclear force and everything, where does that force come? Where does the energy come? Where's the binding power of the energy? Nuclear binding energy. So let's talk about nuclear binding energy, which is going to be that nuclear mass defect answer, right? So the nuclear mass defect is equivalent to the energy released in the hypothetic formation of the nucleus from its parts. So here they have this equation. This is kind of neat how they do this. So we have 8 protons, and the protons, there's one atomic one weight, atomic weight, one proton, one weight onto 8, 1 and 0. This is not atomic weight, I'm sorry. Or this would be actually the nuclear mass, and this would be the charge, because it's +1 charge. So we're going to write it as a proton, 8 protons with 1 proton on positive charge. And so there's 8 with each neutron with a negative charge. Each proton having a positive charge and each neutron having a negative charge. And then each electron here weighs nothing in comparison. So we put 0 and it has a negative charge. So if we look at this with the 8, 8, 8, whatever, but we end up with protons and neutrons and electrons here. So we're going to, if we add up the protons and neutrons and the nucleus, we're going to get 16. 8 plus 8 is 16. Of course, the electron is going to be on the outside, is not in the nucleus, right? So this is 16 with 8 positive charges here. And as we get in here, the plus energy. So this is how they wrote that. That's kind of new. I've never seen that one written before in that way. So, and then the reverse will be true, it says. And here we have the reverse where you have 16 over 8. So that's 16 equal the protons and the neutrons divided by, well, that 8, the charge would be positive 8 plus energy. And that's going to equal back over here. You just switch this around. 8 with the proton, 1 proton at 1 weight, and 1 neutron with a 0 charge, 1 proton with a positive charge, and 1 with a 0 charge, and 1 with a negative charge. Anyway, so. Okay, so for this reason, the energy equivalent of mass defect may be called as this nuclear binding energy, right? So we're going to define, this is a question we need to know, we're going to define nuclear binding energy as the amount of energy necessary to break up the nucleus in its component nucleons. So the nuclear binding energy puts it together, but it's going to take that amount of energy to break up, if you want to break up a nucleus, which a lot of people want to do that. Fission and fusion, right now, breaking up nucleuses. Since energy must be supplied to break up a nucleus, must have less energy than the individual component of the nucleons. The energy difference is equal to the binding energy. All of the energy difference is always going to be equal to the binding energy. So what energy that's going to be released, the binding energy, and what energy is going to be put together. That's a picture right there. So this is the nuclear binding energy. How is this energy measured? Electron volts. So volts, you think of volts, you think of electricity, right? Well, now we're going to think of those tiny electron volts. Because when we're dealing with this, we can't just deal with joules. Because joules are a lot, we're talking down on a minute level. So we have to say a single molecule of TNT releases 6 quintillionths of a joule. And a more convenient union on this atomic scale would be the electron volt. How are we going to measure that? Electron volts is what we're going to use. When we get down here at energy in the midst of a nucleus, we're going to talk about EV, electron volts. And electron volts are defined as the kinetic energy gained by an electron when it is accelerated through 1 volt of electrical potential. That's just what we're going to talk about. So when we're talking about electron volt, what is that? It's the kinetic energy that's gained by 1 electron when it is accelerated through 1 volt of electrical potential. So it's kind of a more complicated, but they did this in a cathode tube and connected it, and they found out in this midst the relationship for joules and electron volts is this, and the detonation of a molecule of TNT produces 35.6 volts, electron volts, so compared to what joules, just the different standards that we're using all there. But also, since nuclear reactions produce far more energy than ordinary chemical reactions, the energy of a nuclear process is often expressed in mega electron volts, where 1 mega volt equals 10 to the 6th of a evolt. So since the mass of energy are related by equation, we must obtain the relationship between mega evolts and the atomic mass. So So in the midst of all this is all, well, what this whole thing is saying, you're like, oh my goodness, I got these numbers and everything. But what's saying, how are we going to measure? And the joule is too large for us to measure what we want to measure at this point. And so they put together another measuring standard. And this measuring standard is through electron volts. But because of the tremendous amount of energy going off when you do set forth a fission process or that type, you're going to have lots of these e-volts or electron volts, and they're going to be changed. So now you need to actually use mega electron volts when you're talking about the nuclear process. Say you're going forth of a nuclear bomb or something, with a lot of energy. So 1 mega electron volts is what we'll measure those in. So just a way of measuring. So binding energy per nucleon. So that the more strongly a nucleus is held together, the more energy will be required to separate the individual nucleons. So if this binding energy is a lot, then it'll be harder to separate. And since all nuclear binding energies are also affected by the number of particles in the nucleus, more meaningful quantity for combining nuclei is the binding energy per nucleon. So you have this binding energy that we've been talking about. And now we're going on and basically talking about the binding energy per each nucleus. So, which is important. Let's go back to see what the binding energy, nuclear binding energy. This is, see the definition, nuclear binding energy. We may define nuclear binding energy as the amount of energy necessary to break up a nucleus into its components. So that's nuclear binding energy. So going back, the binding energy is now, that nuclear binding energy is per nucleon. So why is that? Because some have different amounts of binding energy than others. That's simple. So how do we find out what has more? As a rule, it says the higher the binding energy per nucleus or nucleon, the more strongly the nucleus is held together. So if it has more energy, then it's going to be stronger in holding it together. Harder to take off that bind, right? And so what they did here is they plotted in the midst. And it's very important, this part right here, it talks about, which I thought was interesting because I thought, well, what does this really mean? Binding energy, you can measure it through each molecule. So it reveals that the energy per each nucleon, it goes up rapidly, right? The strength of interaction goes as each element develops more protons and more neutrons. It gets the addition of more. It will have less effect on the increasing binding energy up till carbon-12. So they saw, okay, it changes. First of all, you have these really light elements, and as you get them a little heavier, the binding energy gets strong. But it stops getting strong about around carbon here, and then where does it go? Well, the heavier ones, the maximum strength ones, a lot of times don't unless they're split. So this binding energy can be increased for heavy elements as uranium by splitting them instead. So it actually kind of goes up to a certain point and then goes in the other direction. So that we can see this on this chart. So as we see here, the binding energy of the nucleon as it goes here, you have light, helium's very light, hydrogen, lithium. But as it gets heavier, you're having more energy, binding energy. Lithium, oxygen, still going up. Sulfur, it's still up here. It's 34. Still goes all the way up to iron. At the point of iron, 56, then all of a sudden it drastically, the binding energy of the larger elements start going down. So these become unstable as we're going to uranium. They're getting huge, 238, protons and neutrons. It's a lot. And as they get there, they get more unstable. But if they break apart, they'll go this way. They'll go back up if you break them apart. So this is kind of crazy, but this is the way that energy happens in there. So it's kind of fun to do binding energy per nucleon, which is different. So we see these lighter ones going all the way, so remember, it goes all the way up about to iron, which is at 56 nucleons in its nucleus, right? And then as it goes to krypton, all these become more unstable, and the energy does not get any higher unless you break apart, and then they zoom back up. Okay, so let's answer some of these questions here. From the standpoint of nuclear chemistry, what is the function of the strong nuclear force? So do you remember what that is? So the function is the strength of repulsion between protons is overcome by the force holding the nucleus together. So this nuclear force that holds the nucleus together is 100 times stronger than the force where the protons, when basically like charges, end up wanting to repel each other. But this actually holds the atom together. What is radioactive decay? Radioactive decay is the conversion of one nuclide into another spontaneously with a nuclear reaction. And this nuclear reaction will emits radiation, of course. So basically, radioactive decay is when a certain element decays to the point that it changes into something else. That's what that is, decays. So nuclear mass defect, how is the missing mass accounted for? We went over that, didn't we? So the missing mass is the nuclear mass defect. They didn't know how this was, the mass of every atom is measured less than the mass of the individual particles. And so, okay, what happened then? So that missing mass. Well, basically it's solved with relativity with E equal mc squared, that the object gains mass, gains energy, and energy basically having mass when assembled. So basically you have mass and energy, and that energy overcoming that mass in the midst. What is, let's see, what law states that matter and energy are neither created or destroyed? So what law? That's the law of thermodynamics, or the law of conservation of matter and energy, and matter. The conservation of energy and matter, that it cannot be created or cannot be destroyed. Define nuclear binding energy. How does the energy relate to nuclear mass defect? Nuclear binding energy is the amount of energy necessary to break up a nucleus into its parts. That's binding. What the energy holding it together. And it's the energy necessary. If you need to break it up, we have to break through that energy. How does this relate to the nuclear mass defect? It is the same number, actually. So it's very, very similar to this. The same number, equivalent. It's equivalent to mass defect. Not very equivalent. It is equivalent to mass defect. What is binding energy per nucleon a useful measure of nuclear stability? Yes. The higher the binding energy, the more stable it will be bound together, the more stable the nucleus will be held together. They'll be binding stronger, right? And so this is pretty easy. So you look at which nuclide has the highest binding energy per nucleon. Okay, we have nitrogen with 14. We have iron, which is Fe, with 56, or zinc. Well, we can look up to this chart that we just looked at. And so what did I say? The energy goes all the way up. It's getting, with all these, it's getting higher and higher as these lighter molecules are getting heavier, right? Up to here, and it stops with iron, and then it goes down, and these become, the energy becomes less on the heavier ones, and they become more unstable. So where does this stop? For goodness sakes, it stops at iron. So that means which nucleon has the highest binding energy? Iron. Okay, that's it.